Well, it's such a small room and so few people, I feel like I don't really need the microphone. Anyway, thank you all for coming. I'm James. I work for Thoughtworks. If you haven't heard of Thoughtworks, which there's no reason why you should have done, here's a marketing slide. You don't want to know about that. And here's a lot of books written by some of my colleagues. You might have read some of those books. I haven't written any. It's been pointed out to me that there isn't one on quantum computing yet, but someone's asked me to write one, but I haven't got around to it yet. Does anybody in here know anything about quantum computing? Oh, you probably know more than I do then, so if I get any of it wrong, please feel free to come on stage. We're all quite intimate here. So let's just talk a little bit about Minsk. When I got to Minsk, I didn't know about this thing, obligatory medical insurance. So they wouldn't let me through the border. I had to stand in this queue for ages, and I was thinking, my God, how much is this going to cost? They're going to rob me for loads of money, and it was €4. I thought, blimey, why bother? And then when I got to the hotel, of course, still in Minsk airport, they lost my luggage somewhere in Warsaw. Still haven't got it. So this is the full sum total of all the stuff I've got here in Minsk for 3 days. So is that why there's nobody in the room? Do I smell that bad? Because obviously I'm still wearing the same clothes. So my clicker's not doing great. Excuse me. I'll just stand here and do this. So the hotel said, we can help you out, and they gave me a dressing gown. I don't quite know what use that was, and then of course they looked at me and I said, I've lost all my bag, had all my washing stuff in it. So they're like, okay, no problem, we'll sort you out. So what did they do? They know their customer well. They gave me 6 bottles of shampoo. Thanks for that. And then yesterday I thought, well, I'll try and buy some T-shirts. Well, that's the Presidential Palace, that's this building. I think that's a shopping centre over the road, but I haven't yet managed to go to it. As you can see. And then I thought, well, I get to the conference and normally you get a free T-shirt, so that'll be good. At least I'll get a clean T-shirt. And instead of that, they give me a really cold weather hoodie thing. It's a great hoodie, but I don't think it's really the sort of thing I want to be wearing now. So there you go. And just to prove it, there you go. That's me 2 nights ago, and that's me now. It's not great, believe me. So I fully sympathise with you sitting far away from me. And then last night, we did what we normally do in conferences. There you go. That's the city centre. And I saw this. I don't quite know what's going on there, but I saw this photo on my phone this morning and thought, oh, that's interesting. No idea. I think it might be a kebab shop. And then this morning, I had a little conversation. Somehow, in my state last night, I thought if I take this T-shirt off and hang it on the lampshade, it will somehow be clean in the morning. And similarly, my socks, if I put them on the back of a chair, they'll be clean today. Logical, obviously. Didn't work. So, what are we actually going to talk about? Quantum computing. What is it? How does it work? How is it different from classical computing, as we now call it? And then I've got some stuff about the many worlds theorem, and then we're going to finish off with a story about the quantum in the elephant in the quantum room. Is that a phrase in other languages that aren't English, the elephant in the room? Good. We'll come to that later. So, why am I standing in front of you talking about quantum computing? Well, some more. Oh, you've just doubled my audience. Thank you. So, why am I talking about quantum computing? Last year, in the spring, I was at a conference in Vienna, and I saw this gentleman, Alistair Collinson, who's now a very good friend of mine, talking about quantum computing. And it was a great talk, but I understood absolutely none of it. So I left that talk thinking, I was furiously Googling while he was talking, and I thought to myself, I could do a more beginner-level talk than what I've just seen, because I could see people in the room were kind of not understanding it. Alistair's talk is great, and I recommend you watch it if you fancy looking at quantum computing more. So as I left that conference, the organizers said to me, have you applied to talk to my conferences in Poland? So I was like, no, I haven't. He said, oh, please put something in. We really want you to talk there. So I put in 2 proposals. The first one was about microservices, which was the talk I'd done in Vienna. And as you can see, that was rejected. And the second thing was I made up this talk, which was just, in the quantum fashion, just completely didn't exist at the same time as existing in this CFP. And of course, they accepted that one. So I said to my colleagues, hey, who wants to do a quantum hackathon? I've got 4 weeks to learn about quantum computing to talk about it in a conference. And this was last May. So at that point, I started, well, first of all, I felt like that. And then I started learning about it. I went to loads of conferences. I started organizing some meetups around Thoughtworks. I even did a meetup last year where we had IBM in Thoughtworks office, and they gave us exclusive use of their real quantum computer to submit quantum programs to, which was pretty cool. And then the final triumph, if you've ever heard of the Thoughtworks Tech Radar, where we talk about up-and-coming technologies, the latest, actually this is not now the latest Tech Radar because there's one just coming out now, but this came out last November, and blip number 88 is Q#, which is the Microsoft quantum programming language, which I'll show you a bit of later. And I wrote that blip, which was like, yay. So that's why I'm talking about it. So what is it? Well, I'm going to assume people in this room kind of know how computers work, how classical computers work. And when I say a classical computer, I mean this type of thing that's sitting in front of me. So basically, computers use bits. A bit is conceptually a 0 or a 1. It's two different values, okay? And that picture there is called a flip-flop circuit. Generally, a classical computer holds a bit as two different voltages. So one voltage means 0, the other voltage means 1. And that's how it does it. And then what it does is the bits go through logic gates. So that picture on the left there is an OR gate. The two inputs, A and B, if one of them is true, then the light switch is on, or both true, the light switch is on. This picture down here, these are all logic gates, these are the inputs, and all of that is 16-bit. What that is a representation of 16-bit floating point arithmetic. So when you put together all those gates, push the bits through that, you end up with floating point arithmetic. So aggregating together loads of logic gates is all our computers do. So when you sum that up, you get pretty complex operations like PowerPoint and stuff like that, but essentially that's all computers do. What do quantum computers do? Well, they have something called a qubit, which is short for a quantum bit. They share some similarities with a classical bit. The most obvious one is when you measure their value, you will either see a 0 or a 1. But they actually hold a much more complex value in all the intermediate calculations. You might have heard of collapsing the quantum state. It's hard really to conceptualize, but as soon as you observe the value of a quantum bit, it will be 0 or 1 deterministically thereafter. But until you observe it, it can be holding both 0 and 1 in a sort of probability space, which we'll come back to. The maths is very complex. If you're interested in the maths, check out this talk here, which is a friend of mine in London explaining exactly how the mathematics work. But you can, for convenience sake, For convenience sake, you can think of a qubit as a point on the surface of a sphere. And if you look at that sphere there, wherever the point is represented by psi, it kind of represents the probability of returning a 0 or 1 when you measure it. So if it's pointing straight up, it'll always give you a 0. If it's pointing straight down, it'll always give you a 1. Anywhere else, when you measure it, it might give you a 0 or it might give you a 1, depending on how close it is to one or other of those poles of that sphere. So that's a way to conceptualize it. Don't worry too much about the maths, because I don't have time to explain it. Like a classical computer, quantum computers work with gate logic. So you have some pretty standard gates like X, Y, and Z, which conceptually in that picture of the sphere, they'll just transform through 180 degrees where the thing is pointing to. And then the only other gate that I'll mention, which is quite interesting, is the H gate, which stands for Hadamard. And what that does to that pointer on the sphere is it rotates it through 90 degrees, so it's halfway between the 0 and the 1. So what that does, after the Hadamard transform, your qubit will be in a state of superposition. It'll actually be holding both 0 and 1. So any calculation that takes place on that qubit will actually use both values, which is where the power of quantum computers come in. So essentially, like a classical computer, you've got qubits, you've got logic gates, you have to aggregate them all together to make your program. And I'm going to show you how to do that in a moment. So, if we compare classical computers and quantum computers, well, on the face of it, they're similar. But because of the fact that you're holding zeros and ones in superposition, quantum computers effectively can give you supermassive parallelization of a lot of different computation, and I'll explain a bit more about that later. One of the downsides of them is you can't actually save the state, because if you observe the value of that qubit, it loses the quantum state. It no longer has the superposition. So what that means is there's no concept of persisting states within a quantum computer. So all of your program has just got to run through from start to finish, and then you observe the results. So that's quite a restriction on what you can do. And quite simply, they're quite hard to program. Because so far, we haven't managed to write abstractions on top of the logic gates. You actually need to program against the logic gates. Microsoft are starting to build some abstractions, but they're pretty hard to get your head around as well. So, I'm going to now show you the IBM Q computer. I need to do the thing on here where I do... Oh, God. Excuse me for a moment. I need to do the screen thing, don't I? Screen displays. Bear with me a moment. Mirror displays. Cool. So, IBM has a website called the Ibm Q Experience. If I just scroll up, what we're seeing here is there are 2 publicly available quantum computers. They're in America, both of those computers. They are 5-qubit machines. So that means they have 5 qubits, as you'd expect. And they used to be under maintenance quite frequently, but they seem to have fixed something so that they're not under maintenance constantly now, which is cool. So there's 2 computers there, and you can get an account for free with lots of free credit, and you can start programming these. So, what I'm going to do is I'm going to show you how to program these computers. So if we scroll down here, we see this arrangement. The horizontal lines are, each horizontal line represents one of the 5 qubits. And what you have on the right-hand side there, those are logic gates. So, if I do this, if I grab this X gate and drop it there, and then this thing is a measurement, so I'm going to put the measurement there and the measurement there. When you start the program, all of the qubits, if you think back to that block sphere, they're all set to exactly 0, so they've all got an arrow pointing straight up. If I perform the X transform on one of the qubits, it's going to transform it through 180 degrees, so that qubit will have a value of 1. So, we can now run this program. I'm going to run it on the simulator, because that doesn't cost me any money, and it's quick. So, what happens? Oh God, I've got to give it an experiment name. I forget that every time. What this shows me here is, it's not, can that be seen? That says 00001. Is that visible? So, the first qubit is returning the value 1. The others are all 0, which is kind of obvious because, as you can see, I did the X transform on the first one, and the others I left unchanged. Okay? Fairly simple. Now, that's pretty uninteresting as well. What is slightly more interesting is, oh, hang on, this changed. I need to do that. Now, if I put an H gate on that first qubit, what that now means is that first qubit is now in a superposition of 0 and 1. Okay, so it's holding both values simultaneously. So if I was to use it in a computation, all possible permutations of all the qubits would be involved in that computation. But then I'm immediately measuring it, which sets its value either to 0 or 1. So as well as reading the value, it sets the value. So if I run this simulation now, we'll see a slightly different result. What we see is 52% of the time that it ran the program, it had the value 1, Actually, that's 0. I can see it better on my screen. And 48% of the time, it had the value 1, which is kind of what you would expect, right? Because it's about 50-50 that it's going to give you the value 0 or the value 1. And then if I also drop an H gate on the second qubit in the arrangement, I think what we'll see is 4 different possible results with about equal probability. So there you go. So with about 25, well, you can see that the results are slightly skewed. I'm told that an actual real quantum computer, you can see the results are different that time. So this is a bit closer to 25% for each of the values. Okay, so that's fairly simple. And if you're interested, if you're a Python programmer, which I'm not, if you click on this button here, it shows you in a Python-like scripting language what your quantum program looks like. So you can use the Quasm, it's called, to write a Python-like program. I'm afraid I don't understand Python, so I can't go into that. Okay, has anybody heard of Schrodinger's cat? I'm assuming people have. Now, I'll come back to that other anecdote. Now, down here, I have a Schrodinger's cat simulation, and I'm trying to find the right one. So in Schrodinger's cat, the idea is there is a cat in a box, there's a bit of radioactive isotope which decays. After a certain amount of time, there's exactly a 50% chance that the radioactive decay has occurred. If the radioactive decay occurs, it activates a hammer which breaks a vial of cyanide and the poor cat dies. So what this quantum circuit does is it's simulating Schrodinger's cat. So the Hadamard gate here represents the radioactive decay. So there's a 50% chance that that thing will have decayed. If the Hadamard transform, if the value is read as 1, this is called a C-NOT gate, which is a bit like a classical NOT gate. If the value of the control qubit is 1, it'll flip the value of the other qubit. So in this case, it'll make it 1. So these three, this one is the hammer, this one is the poison, and this one is whether the cat is alive or dead. So the reason why we use this illustrates the C-NOT gate, the Hadamard transform, and then we measure all the values. So what would we expect to see in this? What we would expect to see is either all zeros or all ones, okay? But does that seem reasonable to everybody? So about 50% of the time the cat will be alive, and about 50% of the time the cat will die. Now, how do I... this changes every time I come to the IBM Q thing. I thought there was a way for me to load it in the... Come on. How do I get it to... God damn it. Do I click on it? What does this do? No. Zoom in, export as. I'm trying to basically show it up here, and I can't see how to do it. Ah, there it is. This happens every time I do this talk. I can't remember how to do that, which is a pretty simple thing. So there it is there. So if we run this on the simulator, we'll see 54% of the time the cat lived, 46% of the time the cat died. Now, that's exactly as you would expect it. That's running on the simulator. But if we come back down here, what we can see is, back in October of last year, I actually ran this program. I submitted it to the real quantum computer to see what the real quantum computer would do with it. And I think one of these three, not that one, that's a simulation. That's a simulation, right. So this third one here, I'm going to show you the results of when I ran it on the real IBM computer. You would expect it, again, to be deterministically one or the other. But it's not. What we're seeing there is 37% of the time the cat lived. 29% of the time over there the cat died. And all the remaining results is an illustration of why quantum computers are not yet production ready. They are all errors. They are all things that have gone wrong, because qubits are physical systems of ions floating between magnets. They have to be supercooled because heat coming into them modifies their quantum state, turns them to quantum sludge basically, and heat leaks out every time they go through a gate. So quantum computers are very fragile. And this is what this is illustrating. So it might be better now. I haven't submitted this program to the real computer for a while, but maybe I will do again shortly. Okay. I've gone quiet again. That, I reckon if I do this, yeah, cool. It goes back to sharing screen. No, it doesn't. Preferences. Do I need the microphone in this room?
I think it's small.
Well,
That's fine.
cool. So, oh, now I've got loud again. That was IBM Q. That's my daughter, Clementine, with Clementine's cat. I explained Schrodinger's cat to my daughter, and she said, "Dad, why would anybody do that to their cat?" I was like, no, he didn't actually do that. It's cat. She didn't quite get what thought experiment meant. I'm existing in a state of the microphone not working. It's obviously a quantum microphone. And my daughter, loving cats, of course, the other day when I was in a taxi, I noticed there's a cat museum. So I sent her a link to it and said, "Do you want to go to this museum so you can see her reaction there?" And she's like, "Oh my God, Dad, you've got to go." Well, I haven't gone yet, but if I get time today or tomorrow, I will go. And there's my other daughter, just for fun. So, here's Clementine's cat, again, and this cat is expressing the usual emotion that cats express, which is indifference. And I said to my daughter, what we'll do is we'll run an experiment, because I was learning about quantum computers. Can I impose a superposition of moods on the cat? So we'll see what we can do. And I ran an experiment. I said, what I think we can do is impose many different moods on the cat at the same time, and here's the results. So, as you can see, that was my first quantum experiment. And the very first time I gave a talk, I knew so little about it that was my demo of quantum stuff. I hope I've moved on a bit from that now. This is the Microsoft Quantum Development Kit. This is where I've written most of my quantum code. Okay? This is a language that Microsoft had developed. So, I am now going to show you some quantum code. Oops, how do I stop the presentation? There you go. Some code written in Q#. Obviously, in the great tradition, I had prepared this earlier. Why is this not showing me? Come on, show me the... Oh, there it is. Cool. I am going to use Visual Studio Code. Is everybody... Oh, can you even read that code? Is it readable? I'll make it a bit bigger. Let's see, does Command plus work? Sort of. Is that readable-ish? Ah, it's all on GitHub. There's a link on the next slide. Okay. Well, let's go through the parts of it. In Q#, you have to write two programs. Now, this is because you have to have a classical computer that controls the quantum computer. So, what Microsoft have given us is, here, there's a C# program, which you may or may not be familiar with. I know this is a Java conference. If you just squint slightly, then C# looks kind of like Java. You can pretend on this screen. So, what we've got is, essentially, your quantum program looks like this. This line of code here creates a quantum simulator object. At the moment, that's the only way to run your code. There isn't a real quantum computer that's available for use with this. The idea is, when there is a real quantum computer, that line of code will swap out to be an instance of some quantum computer somewhere in the cloud that you can use. And this is a pretty standard pattern. I'm going to measure something 100 times. And then this line of code here, I've written a program called cat mood experiment, and I'm going to run it 100 times to see what the mood of the cat is. Okay? So the quantum code lives in this file here. And where is cat mood? There it is, measure cat mood. It's a very simple program. I use 4 qubits, one to represent each member of my family. The first qubit is me, the second qubit is my wife, the third my daughter Clementine, the fourth my other daughter Felicity. Now, what this represents is how the cat works, right? In the morning, the cat, I'm usually the first out of bed, the cat comes to me and asks me to feed her. I might feed her, I might not. If I do feed her, she eats the food, she immediately forgets I've fed her, then goes and asks my wife to feed her. If my wife feeds her, again, she might feed her, she eats the food, she immediately forgets, she asks my daughters and so on. So, what I've done in this program, very simple, is to apply the Hadamard transform to each of the qubits to represent the 50% chance that each of us will feed the cat. And if 2 or more of us feed her, she's happy. So, pretty simply, in here, I can run the quantum program. I could if this was a terminal. We're all quiet again. In classic command line fashion, I'm going to do .NET build. If it doesn't build, something's gone seriously wrong. And now I'm going to do .NET run. And what we'll see is 67 times the cat was happy, 33 times the cat wasn't happy. If you do the binomial theorem maths, you'll work out that it's something like a 11 in 15 chance of the cat being happy according to this experiment. I can't remember the exact numbers. So we do it again, and it gave us the same result. It's always disappointing when that happens because people think I've cheated. But there you go, there's a different result, 75, 25. So it's varying about a little gate. And I've just got one more quick program to show you here, which is essentially the same thing, but what this one is doing is that it's pushing down, it's running the simulation, reading the result, running the simulation, reading the result. So instead of pushing the 100 into the iteration inside the quantum program, the C# program is controlling the iteration in this case. And the reason why I've demonstrated it like this is because when we do real quantum experiments, when I was working with IBM, what we were doing was we were iterating over an energy function. So you put the energy function into your quantum program, you read the results back, tweak the input slightly, put it in, read them back. So that's a pretty standard pattern in a quantum program. So in this case, it goes in, it measures the cat's mood, and then outputs the cat's mood. So if I show you in the output window, what we'll see is lots of results. Sometimes the cat's happy and sometimes the cat's not. And if you're interested in this code, you can have a look on my GitHub, which I think is on the next slide, or it's on one of the slides. So you can see sometimes the cat is happy because it's indifferent to our feelings, and other times it's sad, it's still indifferent to our feelings, but she's thinking about moving to another house. So, that is Clementine's cat in Q#. So Q#, of course, is a free download. So if you wanna play with Q#, go to the Microsoft website, download it, and play with it. It's great. I've written loads of quantum programs in it, including some stuff that I will show you later. So, where is quantum computing now? Is that? Yeah, there you go. There's a link to it. Okay. What is the state of the quantum computing art? So, Microsoft claimed at the start of last year that it will have real working quantum computers commercially viable within 5 years. I don't know if they're regretting that claim yet. When I spoke to Dr. Julie Love, who is in charge of the actual science at Microsoft, she was really pissed off that the guy from Microsoft made this claim. This was made by a commercial person. There's a company in America called Rigetti that has real working quantum computers that has, I think, 70 qubits, so you can hire them for a lot of money to do stuff. And in London, I know of at least 2 companies that are writing quantum algorithms and consulting into banks with those quantum algorithms to attempt to predict and optimize financial markets. So what do we need to get a real quantum solution? Scalable qubit foundation. The problem with qubits I illustrated on that IBM machine earlier, they're just not good enough. They leak information out and in, so the technology doesn't exist yet. Microsoft has got one solution that it's working down. IBM's got a different idea. Rigetti's got a different idea again. So these three things, scalable qubits, the interface between your classical computer and your quantum computer, that's really hard to do because classical computers generate heat. Quantum computers are basically destroyed by heat. So the way that that currently works in the IBM machine is what we were showing earlier. The interface is actually microwaves being fired at an ion suspended between electromagnets. That's how you program the thing. So you can imagine that that's pretty hard to do. And error correction is hard to do, as we saw in the IBM case. You need cryogenic systems. That's a solved problem, but they're obviously really expensive. So as long as that's a requirement, we're never going to have quantum computers in our front room. It's going to be a cloud solution. Integration with a cloud provider needs to happen, but as soon as Microsoft or AWS or people have these quantum computers, they're going to do that. They're going to make it happen. And you need algorithms and applications. Well, that's already happening. You can program these computers, I can, and I know the Q branch in London is doing it. So, what's this many worlds thing I mentioned earlier? Well, I'm going to play a video now, and I know the sound is not going to work, but you know what? If you can't hear it, I'll give you some commentary. So, where's the... Here we go. Mirror displays. Where's my video? Here it is. So, we made this video in the Thoughtworks office a few weeks ago. The three of us have been trying to reproduce the double slit experiment. So this is Ben, this is James, and I'm James as well. We've used well, that's me explaining that what we're going to do is the Young's double slit experiment.
Now, down here,
those are my colleagues. That has two tiny little slits in it. That's my laser pointer. I'm going to fire the laser pointer through the double slit.
Here we have
at the other end of the bench.
It's the same laser pointer that I'm going to be using during the
presentation. We'll see it in a moment.
So, who knows, I might
is what I'm going to call a photon detector, which is basically
down this end, we've got
a piece of paper.
We've got Big Ben and medium.
And that's a model of Ben that we did on the 3D printer. Well, I don't know why we used those. That was just for fun. So this laser pointer gives you a red dot like that, see? But when I fire it through the double slits, what happens is we get an interference pattern on the detector, okay? Why does that happen? Well, Young, the man that devised this experiment originally in the 19th century, there you go, there's a better shot of the interference pattern. That's it, just pointing to it, and then that's the interference pattern. So, he devised this experiment because he believed that light traveled in waves, and he was showing that the waves interfere with one another, which seemed reasonable at the time. And will this just work if I do that? Cool. Cool. So light travels in waves, that's why you get this interference pattern. QED, that's what he said at the time. Well, except light doesn't travel in waves. It travels in particles called photons. This is what we now know. But later still, we found out that if you fire a single through the double slit, so one photon at a time, so there's nothing for it to interfere with, and then you detect the photons one by one on your detector, it still builds up that interference pattern. How does that happen when there's no other photons there to interfere with? Well, the answer, according to David Deutsch and various other scientists, is that the photon interferes with ghost photons that go through all the possible paths at the same time, which comes back to this notion of superposition. So the photon is simultaneously going through both slits with differing probabilities depending on the distances, which sounds mad. So it can interfere with itself. Now, that gives us a very powerful notion in quantum computers that there is an interference pattern going on between all of our qubits. And something called the quantum Fourier transform allows us to analyze the results of that interference. So, what you can do you can look at the resonance and the peaks and troughs of those interference patterns, something called the Hadamard transform. The Fourier transform. I don't have time to explain it, and I don't fully understand it. Using those interference patterns gives us massive power to understand various complex dynamical systems. IBM's using it to predict the weather. People are using it to write financial applications that predict risk in markets. But the most exciting thing for me is chemistry, quantum chemistry. This is the iron molybdenum complex, which exists in bean plants. Beans can take atmospheric nitrogen and convert it to ammonia as fertilizer without using any energy. We don't understand how iron molybdenum does that. But using quantum computers and the quantum Fourier transform and some complex analysis of the interference patterns, we're starting to understand these complex organic molecules. Why is that important? Well, the Haber-Bosch process currently uses up to 5% of the entire world's supply of natural gas year on year to produce fertilizer. If we understand how the iron molybdenum molecule works, we potentially don't need this process. And that's the massive price of quantum computers, of quantum chemistry. And that's all because of the many worlds theorem of interference. So I'm going to finish with a quick story. Does anybody know who these three men are? Clue, it's to do with encryption. Yes? No? Okay. No one's ever heard of these three men. We'll come back to them. Anybody know who these guys are? You can probably guess. They are Diffie and Hellman. Okay? So, anybody want to hazard a guess at these three? They do make a very common algorithm between them. Rivest, Schur, and Edelman. They're the Rsa algorithm. Why am I talking about this? Well, cryptography is based on the idea that it's easy to multiply two numbers together, but it's hard to work out what the two factors of a large number are. Now, there's something called Schur's algorithm. This is it. It's factorizing large numbers. You don't just try every number in turn until you find one that works. This algorithm basically shows a better way to do it. And I'll give you an example. If I was factorizing 15, so step one, choose a random number less than 15. In this case, I've chosen 2. 2 is not a divisor of 15, so we didn't accidentally find a factor. Step 3, the period of 2 mod 15. Now what this means is 2 squared is 4, 2 cubed is 8, 2 to the power 4 is 16, which is 1 mod 15. So you carry on raising 2 to the power, it goes 1, 2, 4, 8, 1, 2, 4, 8. So the period of 2 is 4 with respect to 15. Using some simple algebra, what that tells us is that 2 squared minus 1 is a factor of 15. And 2 squared plus 1 is a factor of 15. The crucial thing being half the period. So 2 squared minus 1, 2 squared plus 1 give us the factors of 15. And you can see that in this simple case. So 15 is 3 and 5. Now, I wanted to do a more complex case. So I tried to factorize, when I was going to work one day, the number 1,517. So I randomly chose some numbers less than it and tried to work out their period with respect to 1,517. And it turns out the period of 16, for example, is 45. That's not helpful because 45 is an odd number. So then I carried on, found out that the period of 5 is, there it is there, 180. So that tells me that 5 to the power 90 plus 1 is a multiple of one of the factors, and 5 to the power 90 minus 1 is a multiple of the other factor of 1,517. That's not helpful, because 5 to the power 90 is too big a number for me to do the arithmetic without it overflowing. So I carried on the train, and eventually I found that 14 has a period of 24. Now that is helpful, because 14 to the power 12 does not overflow. So I can show you the actual maths of that back in my presentation, and we'll see that. Here we go. Next slide. Here's the maths working it through. Oh, in my example here, I've actually used 10. Oh no, that's 10 gives us an odd number, so that's me saying, okay, let's try 14. 14 has a period of 24. So 14 to the power 12 minus 1 is this massive number, which is a multiple of 37, which is the first factor of 1,517. And there's the second factor. So it's 37 times 41. The point is, the complexity of finding the factors that way, those periods, is enormous. It's incalculable on any classical computer. But using the quantum Fourier transform, we can actually perform all of those calculations simultaneously. We don't care about all the intermediate results. We just care about the periodicity of it. So, using the quantum Fourier transform, we can unpick the periodicity. We don't care about all the intermediate results. And that is polynomial complexity, which means that that will break RSA. And here's me. Here's my GitHub. There's my implementation of it. I factorized 21, and it took ages, and it crashed my computer several times. My colleague Andrew did a better implementation. There's his implementation there. And he managed to factorize 35 in 2.5 hours. This is because we're using quantum simulators. It doesn't really give us any speed up. Why am I telling you all this? Well, RSA will be dead when we have real quantum computers. It's still quite a long way off, because you need a massive thing, 6,000 qubits, to factorize RSA keys at the moment. So it's a long way off. So as you can see, it's a long way off. So, okay, there are provably secure algorithms that will replace RSA. Now, why am I telling you all this now? Because here's a little history lesson. We're going to go back to these people, and then we're done. This is the known history of cryptography. 1976, Diffie-Hellman published their paper. 1977, the Rsa algorithm was born that we still use today. We all accept that as history, okay? But who are these three men here? Well, in 1997, the British government announced that those three men working for the British government already had RSA algorithms many years earlier than 1977. And of course, it was a secret at the time. So I'm saying to you that there are many governments at the moment that are building quantum computers that we don't know about. Now, not only that, they are harvesting all of our RSA traffic right now, because while they can't factorize those keys today, they can factorize them tomorrow. So I guarantee everybody in this room that that is happening right now. If you want your stuff to stay secure 5 years, 10 years from now, and never be cracked, using RSA will not guarantee that. In fact, I would say exactly the opposite. Using RSA will guarantee that your traffic is not secure. So we need to think about that and start using those provably secure mechanisms of transport right now. And I leave you with that thought. Thank you very much. Do I have time for questions? Any questions? I don't normally get questions at the end of this talk. Yes? Okay, so did you say what should you move to? Okay, there are currently, if I just step back, I skipped over the slide because I was short of time, but there are 3 algorithms currently: lattice-based encryption, supersingular elliptic curves, and symmetric key quantum resistance. These 3 algorithms are a general class of algorithms which are quantum safe. Essentially what they are, Andrew explained this to me, the guy from the earlier slide, because he'd studied it at university. Whereas RSA uses essentially one big number that's hard to factorize, lattice-based encryption uses an algorithm, uses an array of such numbers. And you have to, it's secure because you would have to factorize them all simultaneously and they change. So those are implementable on classical computers and are quantum safe. The top thing there, BB84, what that is a method of, it's like a one-time pad. You use photon polarization to send the key to the person that wants to receive the message. And what that gives you, you make the key, the length of the key, longer than the length of your message. And because you're using polarized photons, if anybody observes the key as it's being transmitted from me to you, that actually breaks, it destroys the key information. So whilst you can't guarantee that an eavesdropper can't read the key, you know if they have. So the idea is you then send the key until you know it wasn't read. Then you send the message using that unique key that you're going to just throw away. And that is currently implemented in sort of closed networks because it uses literally light photons and the polarization of light photons. So at the moment, you can transmit messages over something like 100 kilometers using single photons. And that is 100% secure, BB84. So, but it's perhaps not practical. Any other questions? Yes, sir.
Thank you for your lecture. It's very, very cool. Question is, quantum computers, is it possible that they will be used for the same class of tasks that the classical computers
Right.
or it's just different?
So the question was, will quantum computers be used for the same class of task as classical computers? You could do that, but it would be pointless. Because why would you do that? Classical computers are very, very good at deterministic calculations. There is a whole different class of problems that quantum computers are good at. When I talked briefly about financial markets and about quantum chemistry, essentially what you're doing there is something called an energy function, a Hamiltonian, which defines the ground state of a molecule, and it's really a multivariate, big, long function. And what you're trying to do is optimize that function, a bit like finding the maximum or minimum in a curve. And because quantum computers can simultaneously execute against lots of different values in the many worlds, by examining the resonance of those values, you can jump much more quickly to the peaks and troughs of that function in multi-dimensions. So that's the type of thing that quantum computers are going to be used for, because you just can't do that in a classical computer. There's too many computations. So a different class of problem is the answer. So was there another question? Hello.
Hi, it's kind of difficult to hide any information about the physical architecture of quantum computers. Is it considered a secret?
Okay, so the question is it a secret, the physical architecture? No. I've been to, in UCL in London, there's a lab that I've been inside where they're actually designing qubits. And that's an open project. It's shared across many universities. There's the physical architecture. It's kind of open secrets, right? IBM uses ion trap technology. Microsoft is using something called fermions, Majorana fermions. And the physical architecture of the chips is kind of open source. The IBM ones are actually designed. You can see them. So yeah, I don't think it's secret. It's just that people haven't worked out the best way to do it yet. There's lots of information online. Okay, I've got time for one more question. Yes, sir?
We saw the results of the simulator and actual machines, I think, for the same problem.
Yeah.
And you said that when we executed an actual machine, 37 and 12 and all the rest is a kind of error. And we're trying to remove it. If we remove it, won't we lose something which is very specific to quantum computers? So aren't we trying to make it as a classical one?
Not really. So the question was, if we remove all those errors, will it be like a classical computer? Well, no, because what we're taking advantage of is the interference patterns between all the different qubits. Okay, the reason why those errors exist is because the information is leaking. So we need to get those errors out of there so that we understand that the interference patterns haven't been destroyed. I don't think that's a full answer to your question, but I mean, I'm happy to talk afterwards. I realize that there's so much information there that it's tough to answer all these questions. All right, I think I'm being told to stop. I will be at the party this evening. I'll be hanging around, so if you want to have a chat about any of this, please come and talk to me. It's such a hard subject to get through in 45 minutes, so I hope it was useful to everybody, and you know, thanks a lot for coming. Thank you.